All right, so this is the recorded version of my PhD defense presentation. For those who haven't been able to join in person or online. And the title of my PhD is Urban Greenery and Water Management to Operationalize Thermal Justice. So the big hazard that I've been dealing with in this PhD is heat. And different than other natural hazards, for example, floods that you can really see the water uh, going up in a city. Heat is not something that you can see so well sometimes. And it may mean much more than our rivers here in Switzerland getting packed with people, such as this photo in the limit, but can mean also a large number of deaths in many different countries. So in the world, there's about 500,000 people that die from heat-related problems, and that's not very different in Europe. So Europe also has about 175,000 people that die every year from causes related to heat. And Switzerland is a little bit of a special case because there's about 400 people that die every year in Switzerland, as it's a smaller country and also has better means to adapt and cope to heat. But it's still the deadliest natural hazard in the country, so it's still very relevant for Switzerland. And you may imagine that probably different countries have different ways of dealing with heat, and that also reflects in how population deals with heat. So on the image on the left, you can see an elderly woman just doing some maintenance in her fan outside her home. And on the right, you see a young couple with some greenery around, and they recently acquired air conditioning. Um, so you may probably imagine that the person on the left will suffer more from heat, even though those two situations may be exposed to the same heat event. So people will deal with heat in different ways. And vegetation or urban greenery is one of the things that we can use to help us cope with heat. So vegetation can help cool cities down by two main mechanisms. So one of them is evapotranspiration, so turning sensible heat into latent heat, and also shade, which shelters people from direct sun radiation. So where can we add those green areas? So where can we add those trees? The thing is that, as we saw before, if inequality is a problem, maybe there are places that we should add those green areas first. So what comes to mind is maybe we should add those green areas or trees to places where you have more people experiencing heat vulnerability. Maybe you add this to where you have more space available. Maybe you cluster those trees or green areas together to have a better cooling effect. Or should you add those green areas to where you have more water available, so more runoff water available? And how long would this green areas take to reach peak cooling? So these were some of the questions that I've been through in this PhD, and we will see how that goes and how I went from one question to another along this next few minutes. So in the beginning, I deal with the time that vegetation takes to reach peak cooling. I investigate what is the influence of water and tree amount in that cooling effect. Where should you place that vegetation? We're going to look into a definition of what we're calling here thermal justice, and also a serious game that we created to make this a bit more fun. And then we're going to look to some other further works that will come from this PhD. So first thing I did in the PhD was to use satellite data to quantify the impact of adding new green areas to the city of Zurich. So I used data from Landsat 5 and 8, and basically we found some new green areas that were added within the time frame of Landsat missions. And you can imagine this areas being some sort of a progression in time. So if we look at the differences in land surface temperature in those areas, so what happens in these areas when you add a new green area, we imagine that probably the differences in vegetation will be floating around zero. So the temperature will stay the same as long as you don't do anything. But then when you add a new green area, that temperature probably goes down. And then this is probably correlated to the vegetation amount that you add there. So the NDVI is a proxy for vegetation greenery or health. So whenever you have more vegetation that was added in a place, probably the temperature goes down. So this is what we're expecting to see in the next few results. And what interested us was the time that it took for this land surface temperature to go down and stabilize. And we call this the cooling establishment time. So what we saw was that in Zurich, areas with grasses and shrubs, they would take about 2 to 3 years to reach this peak cooling, this cooling establishment time. And then trees and climbing plants, they would take about 7 to 10 years. So a little bit more, but they will also generate more cooling. But what was very interesting for us in this work was the fact that we saw one of the case studies that we analyzed that had a very low delta land surface temperature, so had a very big cooling effect. And also, this was accompanied by a very short cooling establishment time. So the cooling effect was high, and also this was very quick. And then we went there to see what was going on, and basically was a place that was being irrigated. So that kind of hinted to us that water has a very important role in the cooling of different types of vegetation. So that's what we went to check in the next study that I did. So uh, I then checked what are the urban physics opportunities that you have in a city to understand where trees will cool down the most. So where those green areas will cool down the most, which is very related to the water as we saw before. So the next few slides, you're going to see three different works. One of them will be related to the sphere on the left, the blue part, another work that will be related to the heat risk part, and then another work that will merge these two things together. So when we want to decide where to add green areas in a city, first thing we need to see is where those green areas will cool down the most. So to answer that question, we transformed Zurich into simplified models. So we took the low climate zone classification that classifies the city into surface cover, structure, or material and human activity. And we found three main low climate zones in Zurich, from denser to less dense areas. So areas more in the city center and areas further in the peripheries of Zurich. And what we did was we took those models, and in this space there in the middle that we left open, we added vegetation. So we added one tree, we added a small patch of trees, we added a medium patch of trees and a large patch of trees, and we simulated this to look for thermal comfort. And the way that we simulate this sort of stuff is very similar to what we would see in a wind tunnel. So the picture on the left is not us, that's just an example. So in a wind tunnel, you have, for example, a city or the model of an airplane or something like this, and you blow some wind to it, and you can change the velocity of this wind, and you normally will see something related to aerodynamics or something like that. But in the models that we used, the interesting thing is that we can vary more stuff. So we can vary air temperature, we can vary wind speed, we can vary relative humidity, we can vary radiation around these models. So it's very good for simulating stuff that are related to environmental conditions, and also cheaper than actually building a physical model. And what we simulate, as I mentioned, thermal comfort. So UTCI, the Universal Thermoclimate Index, is the indicator that we used to represent the experience lived by a human being. And this takes into account air temperature, the humidity on this air, the wind speed, and also the radiant temperature around you. So the temperature that the heat that you get from radiation. What did we learn? What were the results that we got? So this is a complex plot. We're going to go slowly through it. So the x-axis is the number of trees, so the amount of vegetation that you add in the middle of those models. On the y-axis, you have the different models for Zurich, so models representing the central areas, low climate zone 2, down to the more peripheral areas in Zurich, and then the soil moisture content in those models. What we learned was that, well, what we want to see here is temperatures going, thermal comfort going from those reddish areas, so the warm colored areas, down to a no thermal stress area by adding trees or increasing soil moisture content. And what we learned was that we only got to a situation of no thermal stress on an average summer day in Zurich if we irrigate the soil completely. So if we really put a lot of water in that soil. And also we need a lower threshold of trees to reach that situation. So we need some trees to add that. And the further you go from the peripheral areas on the bottom to the central areas of Zurich, the more trees you need to reach no thermal stress. And for an extreme summer day, the situation was, of course, even worse. So for no amount of trees or water, did we manage to get to a situation of no thermal stress. So we never got to the point of, we would never get to the point of solving thermal stress probably in Zurich just by means of trees and water for those very extreme events of heat waves, for example. We probably need some other measures. So what does this simulations mean in real life? So how do we take those simulations and actually imagine those trees and water being allocated in a city? So the first thing that we need to do is to look for where you have space available in the city to actually add the trees. Uh, then you need to look into how much water you have available in the city. So meaning that probably if we add trees in places that you already have a lot of runoff water, probably it's going to be better to add those trees in those locations so that you have better cooling. And we also looked into where are the already existing trees. So we don't want to indicate to the city of Zurich to plant trees in places that you already have a tree there. So we also looked into that and calculated thermal comfort for all of these practical situations. The next thing that we looked for to decide where to plant trees after looking at where trees will cool down the most is where are the people that need this cooling the most. So we think that to reach some sort of justice, so to reach some sort of equal distribution, looking for equity, we need a combination of urban physics and also heat risk. So now we looked into heat risk and we looked into the IPCC risk assessment, which characterizes risk basically into four different things. One of them is the hazard itself, so the heat hotspots in a city related to thermal comfort, the frequency of the heat events in a city, the exposure, so where the population is, and if that population is actually inside one of those hazardous areas in terms of heat, and also the vulnerability of this population. And vulnerability is described by two different things, so the adaptive capacity and the sensitivity of a population. So, for example, the population can be sensitive to heat, if it's a population of many elderly people or very young child, for example, but maybe they have the means to adapt to heat. So, for example, have socioeconomic status good enough to buy air conditioning, as you saw in the first images. So when we combine these two things, as I mentioned, probably we will reach some sort of thermal justice, so some sort of intersection between these two things. So to show you some of the results that we got, these are the most important slides of this PhD, I think. So this is what we can give to the city of Zurich as results of what I did. So what we get is into a map that we can score from 0 to 1. Where should Zurich plant new trees if they want to create shelters for people experiencing heat vulnerability? In this map here, what you're seeing are the places in purple that will, if you plant trees in those areas, you actually manage to create a situation of no thermal stress. So you're going to really solve the situation. You're going to neutralize heat stress in full, which is what we're calling thermal justice as capability. So letting people not be under some sort of heat stress. But what is very interesting is that if you add irrigation to those trees, meaning that if you increase soil moisture content, you actually are able to create many more areas that would suffice using trees and using irrigation to fully neutralize heat stress. And this is how the results look like. So our model really gives to the city the places where they could add new trees such that those areas would become heat refuge for people that are experiencing heat vulnerability. And just to give you some numbers, we estimate that if you add new trees only using runoff for irrigating those trees, you would be able to shelter about 27,000 people from heat stress in an average summer day in Zurich. But if you add irrigation to those trees, you would actually be able to shelter about 78,000 people from heat stress, which is basically one out of seven people in Zurich, which is very good. And then we also estimate what could happen if you just add trees, not to fully neutralize heat stress as we saw before, but just to partially neutralize. So we also generated those maps that the city can use to decide where to plant new trees if they want to just improve thermal comfort and not fully solve the problem. And of course, for an extreme summer day in Zurich, the score from our model is 0, simply because there's no way that you can use trees and water to fully neutralize heat stress in those very extreme conditions. And this kind of hints again for the idea that probably we need some other ways to allow people to cope with heat. So places in the US, for example, are creating cooling centers where people can go to spend the night, and places like Barcelona, for example, are adapting existing infrastructure to become heat shelters in those very hot days, which are possible solutions for extreme heat days. When I was doing this work, I mentioned a little bit the thermojustice idea. So in the end, I found myself trying to decide where to add trees in the city. And I was always thinking, like, how can I, as an engineer, make a just assessment, so a fair assessment of where should I add new trees in a city. And then I really digged into the environmental justice literature, and I found some many papers actually trying some definitions of thermal justice. And you can see in this plot that this has been increasing the past few years. Some are attempting those definitions, some are citing the definitions that the parts in blue are attempting, and some are just using the terms thermal justice and heat justice without actually defining those terms. So we thought that would be a good exercise to actually come up with a very well-defined way to represent what thermal justice is based on environmental justice literature. And to do that, we used the environmental justice framework to define thermal justice as a combination of four different things. So thermal justice would have four pillars. The first pillar would be justice as distribution. So this is all more of a philosophical work. There's not going to be any results. The results of this work are just the thought experiment itself. So first thing would be to define thermal justice from a distribution point of view, which is very similar to what we did in our engineering work before. So, for example, distributing trees in a way that is just, so aiming for equity, adding more trees in places where you probably need more trees. There's the second pillar, which is justice as capability. So actually finding ways to identify how those cooling interventions translate to reducing heat risk, meaning that you're gonna allow people to live life in their full capabilities without worrying about thermal stress. And we also did that before in our work. So those maps that show the area where you fully neutralize heat stress, they come from this capabilities background. And it's very important here to use, for example, computational models or sensors to actually measure the impact of what we're doing. And then there are two other pillars. There are more limitations of our work than something that we did before we ended up learning. So justice as recognition, which is the third pillar, says that it's very important that we recognize the groups that are at heat risk, which we did through the IPCC risk assessment, but also identify the characteristics that put them at risk. And before we move to the pillar 4, just to give an example of what are a limitation of looking at a mere distributional justice perspective. So for example, if you want to add a new vegetation in a city and you misrecognize the problem as just a mere lack of vegetation, you add new green areas, but you end up, for example, creating some sort of green gentrification where residents are displaced to other areas. And that means that heat risk in a sense is persisting, but it's just persisting somewhere else. So you just displace the problem from point A to point B. But if you recognize the root causes of why people are experiencing heat stress, in this sense here, in this example here, probably because they have a low socioeconomic status, and this was the only neighborhood that they could afford, which by definition has a low amount of green area. You would need to accompany the addition of green areas with other anti-displacement policies. So, for example, social housing or freezing rents or something like this, such that residents can stay and cooling is actually delivered. And then on the final pillar for this, we looked into justice as participation. So this point of view indicates that it's very important for you to incentivize the participation of the affected population when you're deciding, for example, where to place trees. And this is something that we didn't do in our process, but we ended up later incorporating this into a game. So we developed an educational game that was the most fun part of my PhD, which is to address the participation limitation. And the goal of this game is very simple. So you use cooling technologies from the intervention card decks to shelter people who are at heat risk and put them into a situation of no thermal stress. The game really transforms heat governance, so decisions related to heat, into a collective decision making. People have to deal with the trade-offs and decisions on this. So we played this game in 3 different countries, in Zurich, Brazil, and in Colombia, and it's been really, really fun. So coming to an end, overall takeaway of what I learned in this past 4 years of my life is that green areas, they do take time to reach peak cooling. We really need to act as soon as possible. Trees can mitigate heat stress as long as they have enough water to mitigate that heat stress. Space and water are very big practical limitations for tree cooling. So in city centers or in places where you don't have enough water, this can be a huge limitation to actually get the best cooling out of green areas. To reach thermal justice, you need some sort of combination of heat risk analysis and urban physics, as we saw in the definitions of thermal justice. And most important of all, I think what I learned is that science is not done until we communicate it and we can engage with people's participation. What I would do in the future, if I had more time, I would scale up this work that I did only for Zurich, but to the whole world if I could, and also integrate other cooling technologies and not only trees, which is what I studied the most. I would better integrate water reuse, for example, or think of ways of storing water to deal with mismatches between when you have more water and when you have more heat in throughout the year. I would incorporate better the game into the decision-making process that we saw before, and also expand my work to other species, not only the human species. So develop multi-species thermal justice and also evaluate some other co-benefits, and also account for other policies that could come together with the cooling technology placement to account for heat risk displacements, for example. So come to an end, and I would just want to say thank you to lots of people. First to my supervisor, João, Max, Peter, that were very close to me throughout this journey. To the committee members that came here to evaluate my work, Alex and Denise, to the Swiss National Science Foundation, to ETH Zurich and Eawag that hosted this work, and to all the amazing friends that I made throughout this time in my samba groups, in the people that went to the mountains with me, in my colleagues and friends at Eawag and ETH Zurich, my friends back in Brazil, and most important of all, my family, my father, Valdir, and my mother, Silene. Thanks a lot.